I'll be right back.
Sure.
My wife said I had to change my shirt.
Well,
I do what I'm told.
I checked with mine on this shirt, so. So yes, I will be monitoring the chat window in real time. We are live, and so we have looks like one person who's early. Hopefully we'll see who comes in a few minutes.
Oh, it's going to take a while for this to catch on, so if there are only a few people, that doesn't disappoint me at all.
Well, if that's the case, we could have the chat just the two of us. It would have fine evening doing that. I will record this. I'm not sure if we'll ever use it or make it available to anyone, but if someone says, gee, I sure would have loved to see that, and Doug Duncan says, I missed that, could you show me a recording? I will have one.
Doug and I were actually roommates as both graduate school for a while and also as postdocs. So I've known Doug a long time. He was 1 year ahead of me at Lick Observatory.
Did you meet him at SSP?
No, we were grad students together. So he was the one that recruited me. He started in 75, and in 76 there was an opening. He said, Nick, you really like doing this. And I was like, yeah, what's not to like? Get to hang out with really bright students and be an Ojai. And the way Doug talked about it, it was So excited.
Oh, he
It turned out
recruited
it
you to
was.
SSP.
So he brought me down to SSP in 76. He wasn't there in 77, but I was.
Right.
And Carl was there, and Tim Erickson, I think, was there.
Yes.
And Alma, of course.
I haven't talked to Alma in a long time. But we're having a dinner in LA in September, and hopefully she can come to that. We're going to actually, the theme of it will be honoring SSP faculty. So we'll try to recruit her, buy her a free ticket to that.
I think one of the high points for the students was watching George A. Bell draw a circle. He had this ability to stand with his back to the board and put his arm out like this and do a perfect circle with a radius. And students just loved it. I mean,
a photo of that. We made a refrigerator magnet out of it.
Okay, yeah. That's yep, that's George.
This may have been 76 that this was taken, actually.
It kind of looks it's about that time.
Yeah, and this is a quote from an interview he gave in the 70s, I think. He talked about the summer science program. The summer science program began in 1959. Everything went wrong that could possibly go wrong. It was complete chaos and enormously successful. So I love that quote.
He's a great guy. And everyone knows his name in astronomy, even if they didn't know George, because the Abell clusters that he identified for his thesis and then later on. So it's
absolutely
Abell.
Absolutely. He was not on the faculty in my year in 74. He was off that year and just came as a guest speaker. So we got to see him once, but that was all. So, all right, we have, well, we'll just wait till 8 o'clock sharp, 2 minutes to go. There's 7 watching now. So that's some early folks. You could type into the comments and say hi if you care to, folks. We can't see you, but you can type in, we can read what you write. Maybe that would be a good idea to at least know the chat is working in YouTube. Aha, we do have our first chatter, and we will get to Stanley's questions shortly when we start the program. I don't think you can see the chat window unless you open a YouTube browser window, so that's fine. And they can't see your chatting. I'm only with you on Zoom, so.
I realized that after I typed it in my Zoom chat. It's like, this is not going anywhere except to Richard.
Right. So I'll introduce you when we start officially. All right, let's get started. 8 o'clock Eastern. Welcome to the first SSP Ask Me Anything. This is an opportunity to get to know and learn from, in this particular case, Dr. Nicholas Suntzeff, but we hope this will be the first of a series of these. We're going to wait until the summer's over so we can have our regular guest lecture series uninterrupted and without competition. But then after that in the fall, we'll try this again, assuming that it goes well, which I think it will. If you care to nominate someone who has an SSP connection to be a future Ask Me Anything guest, then by all means, let us know. You can email us at sspalum@ssp.org, and we will compile a list of future guests to Ask Me Anything. For tonight, We ask you to type your questions into the chat in YouTube, and we don't know if we'll get to them all or not. It depends. We don't have a hard stop at in an hour, but we don't want to keep going forever. So we'll see how things go. Nicholas Suntzeff is chair of observational astronomy and director of the astronomy program at Texas A&M University. He is an observational astronomer specializing in cosmology, supernovae, stellar populations, and astronomical instrumentation. Nick grew up in California, majored in math at Stanford, then earned his PhD in astronomy and astrophysics from UC Santa Cruz. In between those two degrees, Nick spent the summers of 1976 and 77 at the summer science program in Ojai, working as a TA under George A. Bell and Dave Pierce. He returned as a guest speaker in 1984 and then took a break to live for 20 years in Chile, and then came back and has been a guest lecturer for us 7 more times since 2007, including later this summer. So when we thought of holding an Ask Me Anything series for SSP alumni and friends online, I immediately thought of Nick as the ideal person to invite first, because after all, he studies the entire universe. So with that in mind, welcome. You care to say a paragraph of introduction to your work, Nick?
Yeah, but I'd like to say just a few things. First of all, I was a TA in 76 and 77, and it was one of the most wonderful, memorable times of my life. I mean, most of you watching are probably students, and so you had a particular experience. But experience as a teaching assistant, kind of in between the students and the faculty, it was a marvelous time, and we got to know you guys. You guys are so bright, and one of the things I find in teaching at a university is that there's a core of students who are just interested in things and just want to understand how the universe is put together, or details about history, but they're wide open to learning about stuff and figuring stuff out. And that's especially what SSP students are good at. They figure stuff out and they like doing that. Somehow we beat out of the teenagers in our society the joy of just figuring stuff out. One of the times when I was at Caltech, I met Richard Feynman a number of times. We'd go down on Friday and hang out at the Athenaeum, and there was one room where Feynman would be, and we'd talk with him. And he said, someone once asked him, what is doing science? And Feynman, I don't remember his exact words, but they're essentially the following. He said that science is figuring stuff out, but not fooling yourself at the same time. And then he paused a while, and then he said, and the hardest thing is not fooling yourself. And I always thought that was a very good quote. And it is what I saw in the students at SSP. They really enjoyed figuring stuff out. There are things you didn't enjoy. I remember Besselian interpolation wasn't real fun, and using the measuring engine to measure the asteroids, but it was a blast for all of us. So you're part of a larger program of really very special people. And the students that I've met since then, almost all of them still have this joy of just trying to understand things. So I enjoy coming back every year to SSP and getting to meet the students and getting to meet the TAs and the professors, and reliving those feelings of what it's like being around the best students in the United States in science and technology. So what I'd like to do is, as an introduction, is just talk a little bit about the universe. I am severely dyslexic, and so I have a hard time spelling and writing things. And so I tend to think of things in cartoons, and that making a cartoon in my mind of what stuff is has really helped me in cosmology. And because I have these cartoons in my mind that I can kind of link together like a jigsaw puzzle, I think I understand the feeling of what it is like to be living in our universe, because I have this mental image. So I'd like to describe a little bit of the universe as I know it. The problem is the word universe is very vague. It means everything, but what is everything? I mean, is it everything we see? Is it everything that we could see in the future? Is it everything that we'll never see, but we think is out there. What defines the universe? And so over time, I've discovered that in astronomy and cosmology, when we use universe, we're actually talking about three different things sort of simultaneously, but we don't give them different names. We just call them the universe. And I think that's partly what confuses a lot of people when they read a popular book or try to figure out stuff about our universe. So let me just explain a little bit of the cartoon that I have in my mind. First of all, we know the universe has an age. It's clearly between 13 and 14 billion years old. There are 5 independent ways of measuring that 4 of them are based on the 4 fundamental forces, different fundamental forces of nature. They all give you the same values. So we've nailed the age of the universe up to the problem of what the speed of light is. But if there's speed of light is variable, then which is almost impossible to measure, then all bets are off. But we don't think that's the case from indirect evidence. So we know the universe has a certain age. So that immediately says the universe has an edge to it. And that edge is not a brick wall, which you can't travel beyond. That edge is an edge in time, because anything that's farther away than that, the light hasn't had time to get to us. And so it's not in our observable universe. So our universe is also expanding, which makes it complicated. So those two things put together, the age of the universe is a finite age and it's getting older every second that I talk, and it's, excuse me, and the fact that it's expanding, and every second that I'm talking, it's expanding more and more, makes it hard to describe how to measure distances. So let me tell you the easy way of measuring distances. This is what we call in cosmology a proper distance. And what you do is you take the universe and suddenly stop everything. Stop it from expanding, just freeze everything. And now you give yourself the ability to jump anywhere in the universe you want to, which of course you can't do, but that's in our mind's eye, think of that way. So we've taken our universe, we've completely stopped it, and now we're going to poke around in this universe and we're going to explore it. So in terms of proper distances, the universe edge, looking backwards in time, is about 13.5 billion years old, depending on what value you think the Hubble constant is. But the universe has expanded a lot since then, and we've now stopped it from expanding. And now if I actually measure the distance from here to the edge of the universe in this expanded universe, it's about 40, 50 billion light years in radius, because the universe has expanded a lot in the last 13.5 billion years. So that's one sense of the universe. Okay, so now let's unfreeze the universe and let it start expanding a little bit more. And as it expands, we can see farther back in time, but also at the very edges of the universe, new galaxies begin to appear, because over time, our universe is expanding into something that's larger. And that something that's larger presumably has galaxies in it, just like ours, because over the last 13.5 billion years, we've expanded, we know we've expanded into something that continues to have galaxies in it. So if it's been doing that for 14 billion years, it's going to do it for another billion years or so. So immediately we have two problems. We have an observable universe, but we also have something that we're expanding into. And so over time, the number of galaxies in our universe is going to get larger and larger. Right now, we have about 2 trillion galaxies in our universe, depending on whether you want to count the wimpy little galaxies at the edge of the universe or not. So think of the universe, we've started expanding again, and it's like we're expanding outwards into something else. It's kind of like throwing a rock in a pond, and you're watching the ripples go farther and farther out from where you drop the rock. So long as the pond is very, very big, the ring just expands and it encompasses more and more of the surface of the water. Same with us, except in 3 dimensions. This observable sphere around us just grows in size, and more of the larger universe comes into view. So those are 2 universes that are intimately related. What we can observe, but we know what we can observe is smaller than what we need to describe cosmology. So another thing that now enters into it, which is really confusing, is if we go back to this concept of proper distance, and we've frozen the universe and then we let it go and we follow how that proper distance stretches, in those coordinates, the universe between those 2 points can actually begin to stretch faster than the speed of light. nothing, it's an illusion. The galaxies that look like they're moving away from us are actually not moving. So the universe is stretching in between the two. So if something stretches, begins to go faster than the speed of light in these proper coordinates, you're not going to be able to see it anymore. So as the universe expands, if it accelerates, if it's going faster and faster and faster, sooner or later, we're going to lose the edge of the universe as we see it, because the most distant galaxies are going to begin, the universe is going to be stretching faster than the speed of light to those distant galaxies. So we have a universe which is expanding but slowing down. And we now know there's something called dark energy, which is causing the universe to really, in a wacky way, accelerate faster and faster. And though now if we add that into it, there's a complication, because now the universe can stretch faster than the speed of light. So let's go back to the idea of the proper coordinate system. We've frozen the universe. But now we can also see infinitely in all directions into whatever this larger universe is. So within about 13 billion light years of where we are right now, all of the galaxies we see are emitting light at this age of the universe, and that light will sooner or later get to us. So all of the galaxies within 13 billion light years of us, we will someday see in the future at an age of 13.5 billion years old, the age of the universe today. From about 13 or 15 billion light years out to 46 billion light years, those galaxies are emitting light right now, but the light they're emitting right now is never going to get to us, because the stretching of the universe is going to go faster than the speed of light. So we can see them today, and they're younger because it took light to get to us, but we will never see those galaxies as if they are as they are today. That light is never going to get to us, but we can see them right now because that light left a long time ago. So that goes out to about 46 billion light years. From 46 billion light years to about 65 billion light years, those galaxies we can't see right now, but as the universe expands, those galaxies are going to come into our field of vision, and we'll be able to see them. Of course, we'll never see them when they're very, very young. So we have these different shells, and outside of about 65 billion light years, we'll never see any of that stuff. It's presumably there are galaxies out there, but that light is never going to get to us. So we have this kind of onion skin of what we can see in this universe, which I've frozen. And so the universe that we're comfortable with, our observable universe, we'll see those galaxies mostly when they're the age of the universe. So that's a kind of a simple concept of the expansion of our universe, that there are, because the universe has an age, because it's expanding and accelerating, and we know in the past that we have been expanding into something that's larger, we require at least two universes: the observable universe, everything we can see, and something that we're expanding into. So I'd kind of like to stop the discussion there, because I can go on in many, many different directions. But that's the essence of what we know about our universe. Oh, if I may say one other thing too. So if we take, since the universe has been expanding, if we run the clock backwards and we take everything we can see in our observable universe and run it backwards in time until it gets to a particular temperature, which is a gazillion degrees, it's called the Planck temperature. That size of our universe, everything we see in the universe is about the size of a beach ball. It's about half a meter across. So we call that in astronomy the Big Bang. The beginning of the observable universe is when our whole universe is crammed down into something the size of a beach ball. Indirectly, we can measure the minimum size of this thing that we're expanding into, which I call the meta-universe, and that is about somewhere between 100 and a kilometer in diameter. So we're a little beach ball size inside something that's like the size of a gigantic tank of liquid gas that you see in places that are distilling petroleum. It could be much larger than that, this meta-universe, but it has to be at least that size. And that's a measurement that's actually not that difficult to make. So I can give you two sizes to the universe when it's formed in the Big Bang. One is the observable universe, the size of a beach ball, and the thing that it's expanding into, which is at least about roughly 200 meters across. So with that as an introduction, please go ahead and ask me questions.
Okay, we do have some questions in the chat already, not too many, a few. Let's start with Stanley Sokolow. Are the orbits of stars and galaxies stable other than local perturbations, or rather do the stars gradually spiral into the galaxy core and hence be consumed by the central black hole? And if that happens, does that imply that the galaxies eventually become invisible as super duper black holes?
Good question. Just imagine that you have a bunch of stars that are swirling around like this, and you send in a star from the side into this swirling mass of stars. Stars will never collide with each other. But as this star from the outside goes into this group of stars, the mutual gravitation between this one star that's coming in and all these other stars will cause the stars in this cluster to begin to accelerate towards the direction that the star is moving. And so as the star is moving through these stars will absorb some of the energy of the star that's moving through it. We call it gravitational friction, and that star will slow down. So the net result is the star slows down, but the stars in the whole group begin to speed up a little bit because they've absorbed the energy of the star going through. So there's also gravitational friction in galaxies. It works in both directions. Some of the gravitational friction actually causes stars to slowly move inwards towards the center of the galaxy. But there's actually an opposite effect in the disk of our galaxy due to the fact that there's a bar structure in the middle of our galaxy, a bunch of stars that are not spherical, but kind of cigar shaped. And that thing is kind of like a rotor that goes around and mixes up the galaxy. And that actually drives the stars outward. So our sun, when it was actually born closer into the center of the galaxy than where it is today. But we do have this gigantic black hole in the center of our galaxy. Two people won the Nobel Prize for the study showing that it's 4.6 million times the mass of the sun. That black hole certainly will eat stars, and we see in somewhat nearby galaxies, we actually see the centers of galaxies suddenly flaring up and then going away. And what we think is happening is the black hole is eating a star, and we're watching the black hole just rip this thing apart as the star falls into the black hole. But you have to aim the star almost directly at the black hole for it to be able to eat it. Things can just orbit around the black hole with no problem. So we're left with the fact that we know there are big black holes in the centers of galaxies, but they don't eat very many stars over their lifetime. And yet the black holes in the early universe are smaller, and the black holes in present universe that we see around us are much larger. So they've grown, but how have they grown? They haven't grown by eating stars. And the only thing we can come up with is that the galaxies cannibalize each other. And so two galaxies come together, the stars end up mixing together by friction, and the two black holes in the center end up spiraling in and forming a larger black hole. We can push that back into the early universe, but we come across a problem in that we still need a first population of big black holes. We have no idea where this come from. So that's one of the big mysteries in the study of the formation of galaxies in the universe. What produced the black holes in the first galaxies that were forming? Because there had to be a seed black hole, and there are all sorts of theories, but there's we're not agreeing on any of them.
Speaking of black holes, other than black holes at the center of galaxies, which tend to be large, are there small black holes? Is there any mechanism for forming smaller black holes? And so how would you find them?
Well, the smaller black holes, by small, we certainly can find black holes the mass of the sun or so, if they're orbiting another star. And those black holes would be a couple kilometers across, and we can see the gravitational effect just of the fact that there's an object that isn't giving off light going around an object that is giving light. So you'll see the object giving off light kind of go back and forth like this. And so we can measure, we know that there are black holes down to about three to four times the mass of the sun.
Because they were massive stars that went supernovae, and what's left is a black hole.
Yes.
Is there any other process that creates black holes smaller than that?
They're exotic processes, but not ones that we think can actually occur, but maybe they do in exotic forms. Now, at some point, the black hole gets small enough that because of something called Hawking radiation, the surface of the black hole actually radiates as if it has a temperature. And the smaller the black hole, the higher the temperature and the more it radiates. So something about the size of an asteroid, which would be minuscule because it's a black hole, that thing will evaporate all of its energy in about the age of the universe. So those things, we can sort of rule those out because first of all, we'd see this flash of X-rays, but also they'll evaporate in 14 billion years. But between the size of a planet and the size of a couple times the size of the sun, that's a really interesting area that we don't know how those form, and we haven't found any, but we can't rule them out. We should keep an open mind.
And I noticed in your lecture last summer, you had a slide adding up the different kinds of mass in the universe. And there was something like 4%, what you called ordinary matter. I don't recall black holes were even listed there. Is that because they just don't make up that much of the total mass?
No, they don't. They're negligible in the total mass. So 70% is dark energy, which is driving the acceleration of the universe, and it's an anti-gravity that Einstein predicted but threw away. We have no idea what that is. And any attempt to explain it gives us the wrong answer. That's crazy. And then about 30%, a little less, 26% is dark matter, which we see the gravitational effects, but we don't see what it is. And 4% is just normal stuff like you and me, protons and neutrons and electrons. But of that 4%, most of it is in a thin gas between the galaxies, which you can barely see. And in terms of stars and black holes and everything else, that is about 0.5% of the universe. So when I look out with a telescope into the universe, I'm seeing only 0.5%, and I'm missing 99.5% of what's out there with my optical telescope. Kind of annoying. But no, why do we live in a universe like that? How weird.
Speaking of the universe accelerating, is expanding faster. That's not what I was taught in the 70s in astronomy. That's something that you and your colleagues discovered, and it was not, as far as I know, expected, but maybe it was. Is that something that how long did it take you to believe that result, that the universe is not slowing down, it's actually speeding up? What was the thought process that went through your mind, your colleagues, when you were concluding that that's what your observations were telling you?
Well, what went through our minds is I sure hope we're not wrong, because we're going to be embarrassed for the rest of our life if we get the
It'd be cold fusion all over again.
Yeah, it'd be cold fusion all over again. No, there was an inkling, more than an inkling, that there was this dark energy before. It wasn't called dark energy, but they called vacuum fluctuations. And actually, vacuum fluctuations were included in cosmology in 1933 by the great cosmologist George Lemaitre, who was both a PhD physicist at MIT, but also a Catholic priest in Belgium. And in order for him to create a universe, which he called the primeval atom, which looks basically just like the Big Bang, he actually introduced dark energy in 1933. So it's been around a long time, but it's just kind of been ignored because it just doesn't make any sense. But the problem in the 1980s was that astronomers were beginning to measure the ages of stars very accurately. And the ages of stars were beginning to appear older than the age of the universe. The universe was just normally expanding and slowing down with just matter. So you can't have stars older than the age of the thing in which they're living, the old universe. So the way to get around that would be to add in this dark energy, this acceleration. And there were a couple of other hints along those lines, but no one really stuck their neck out seriously and said, this is the solution to this problem. There were papers written on it saying, well, this is kind of neat. This will explain everything, but it doesn't, clearly it's not right because it doesn't make sense. So we we knew that it was not out of the question that we would be able to find something like acceleration, but we certainly didn't think we were, but we had an open mind for it. So in the end, it was just measuring numbers, and with a dark energy, the universe is bigger than it would be if it was just normal gravity. So all we found to prove dark energy that won the Nobel Prize in 2011 was that galaxies were about well, the exploding stars in these galaxies were about 20% fainter than they should be, which meant that they were farther away. And that was the evidence for the acceleration of the universe. But it's pretty easy to measure the brightness of something to an accuracy of 20%. So it was really a simple thing to do, but no one had done it before. And so we were just lucky that we were the first to do it. And I think because it was such a simple observation, many people just jumped on the bandwagon and said, oh yeah, these two groups who got the same result must be right.
Well, speaking of simple observations that no one had bothered to do before, the cosmic background, microwave background radiation would be in that category, I would think. And we have a question from Ed Finstermacher. As the universe has expanded over the past 13 million years, the CME photons have stretched and now each have roughly 1,000th of the energy they originally had. Where did the energy go?
That's a question that I hear all the time. Where did the energy go? It's this one always stumps me how to explain it. This unfortunately, this is one that I don't have a good cartoon in my mind. Some cosmologists will say, well, it goes into work in the expansion of the universe, but that's not true, because you can't define a total energy of the universe inside the theory of general relativity of gravity. So the idea that it's the energy goes down because it's doing work in the universe is mathematically not correct, although you'll read in books some people saying that. So what is any photon that we see in the cosmic microwave background radiation has traveled straight to us, except for a little bit of warping due to gravitational effects. That photon has traveled to us straight and has not hit anything. So we have this clear view backwards into the universe of what we call the cosmic microwave background radiation. That's the point at which the electrons and the protons are beginning to combine. If you go back earlier, the universe is hotter and the electrons are flying around free, and light can't get through electrons that are flying around free. So the universe is opaque. It's kind of like a flame. So there's no flame in the universe as we look farther and farther back, and the universe is smaller and smaller. But at this one magical time at about 3,000 degrees above absolute zero, the electrons, as we go backwards in time, are stripped off the protons, and things are freely flying. So we have this photon that is coming directly from there to here. And what is happening to it? Well, it's the same thing that's happening with time dilation. What you're really seeing is a general relativistic effect that as something is coming through a gravitational field, time slows down. So the way that we get around the question, and I'm sorry, this is not very satisfying, and I admit it's not satisfying, but this is the best explanation I have right now. But I'm continuing to try to find a way of explaining this better, is that you're not seeing the energy go down per se. What you're seeing is the fact that the time is being dilated, time is slowing down. It's the same idea as I'm saying the galaxies are not moving away from each other kinematically. They're actually the same position, but the universe is stretching in between the two. There's no energy involved in that stretching, but it is apparently the universe is stretching in between the galaxies, so it looks like the galaxy is moving away. Same thing happens with the photon. You can't define energy of a single photon uniformly from last scattering till today. That's not something you can do in general relativity. So we go back into these mathematical equations of Einstein and we say, just like the universe is stretching, but there's no energy involved in it, the universe is stretching those photons, but the photons, the energy, you can't compare directly that photon early in the universe until today. And I'm sorry, that's the best explanation I can come up with. And I know it's unsatisfying. But don't believe it that when people say that the light that's coming towards us is doing work clawing up the gravitational field to get to us. It's not doing any work.
Okay. Speaking of relativity, Stanley had his original question. I've heard that the GPS system depends upon relativity. How so? It's kind of a technology question, but it's related.
That's a great question too. When the engineers were building the first GPS in the 1960s, they were interested in well, there are many reasons they were interested, but it was all national security, and they asked the physicists, okay, well, how do you, if you put a clock up there, how do you keep it synchronized with everything else? And the physicists, just like the last explanation I gave, said blah 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 blah, and it didn't make a lot of sense to the engineers. But the physicists were saying, well, you got special relativity and you got general relativity. You got both of these things. You put them together, and you've got to have this correction. And the engineers thought, well, that's general relativity doesn't really affect any of us here on Earth. We're not including that in any of our calculations. So they didn't believe that the general relativity effect, the warping of space and time, would have any effect on the clocks. So they actually had two different types of circuits. They had one that just had special relativity and one which had special relativity, which is included in general relativity. And the physicists were kind of in our arrogant way, well, saying, well, you'll figure this out one way or the other. And sure enough, they launched the thing. They look at the special relativistic effects, and they can't measure a position on the surface of the Earth to better than about 1 kilometer. But when they turn on the general relativistic effects, then they could get down to the predicted accuracy of the clocks. So the effect is that a clock high above us is in a lower gravitational field, and therefore when they look down on us in a higher gravitational field, they see our clocks as running more slowly. And it's that difference that's called time dilation. The difference, it's a small difference between the clocks ticking here and the clocks ticking up there. They'll tick the same when they're here, but you move that one up there, and this one now thinks we're ticking more slowly, and vice versa. So it was a surprise to the engineers that they had to include general relativistic effects, but they definitely do, because you can't get anything accurate using just special relativity.
All right. Sometimes the engineers need to defer to the scientists.
Not usually.
Engineering is applied science, after all.
Yeah, but as I like to say in my astronomy class, one of the good things about astronomy is if you make a mistake, no one dies. You can't say that if you're a surgeon or an engineer in many cases. So if we're wrong, who cares? But if you're wrong, you're a mechanical or civil engineer, it's like, that bridge may collapse.
Another thing I noticed about astronomy in college is that often they assume pi is 1 for simplicity.
Not only that, they assume 2 pi is equal to 1. That one always really irked me. You can't, but yeah, you just like, yeah, it's equal to 1.
A question from Mihaela Froelich, and I apologize if I mispronounce. What number of planets would be the most a specific star has?
Ooh, good question. We don't really, well, there must be a number. I'm not an exoplanet expert, but if the planets are too close together, you begin having gravitational effects between 3 different objects. And when you have 3 different objects that are close together, 2 of them will fall into a gravitational attraction, and that liberates energy that appears in the 3rd object, and that gets flung out. So you will have what's called a 3-body interaction if the planets are too close together. And I actually never even thought about that, but the idea of 3-body interactions must put a limit on the number of planets of a given size in a solar system. There was an extremely important paper published a couple of weeks ago headed by a professor at Caltech that showed that the solar system that we have, where we have these small planets in interior and the gas giants, out to 10 or 20 times the distance of the sun to the Earth, turns out that's probably the most common form of solar system where you have multiple planets, having gas giants farther out and having rocky planets farther in. We certainly know there are systems where the Jupiter thing is close to the star, but we think it's wandered in. But if you look at the average solar systems that have been discovered till today, it looks like our solar system is actually a common form of solar systems, more common than other ones that we've seen in the early studies of exoplanets.
Well, we prefer to think we're special, Nick, so I don't know if I accept that. Let's move on to another question. This is a reference to your lecture from last summer, which we offered for folks to watch. This is from Jared Mochtinger. In your lecture from last year, you implied you were very confident the universe is not a simulation, but you didn't have time to explain. Could you please explain why you think that?
Maybe my confidence is overstated, but the thing is, if it's a simulation, there have to be round-off errors. There's not an infinite amount of information in the universe. And as a matter of fact, almost all the information in the universe sits on the surface of black holes. If you ask where, if you think about where stuff is, where that atom is over there, where that atom is over there, and how they're associated with each other, you add all that stuff up, that's called entropy. And the most entropy in the universe, weirdly, is on the surface of a black hole. Stephen Hawking and a guy named Bekenstein showed that. And so a black hole is like a computer disk. And the surface of the black hole, information gets stored or gets frozen at the surface of the black hole. And there are little pixels, little memory units on the surface of the black hole called Planck lengths, which are very, very small distances. And so most of the information in the universe is there in those black holes, but it's a finite amount of information. So one would expect that if we're in a simulation, you would begin to see round-off errors. You can't have pi to an infinite number of digits. So yeah, the aliens who made this computer program may be expecting that we're going to start asking the question, why are there no round-off errors? And then if you bring that up, then I'm obviously not confident. But computer simulations have to have round-off errors. And there's a finite amount of information that you can put into a computer because the universe has a finite amount of information. And almost all of it's in a black hole.
Okay, that's reassuring. Question from Martin. This is a kind of planetary astronomy, perhaps, but the question is, regarding the poetic notion, we are stardust. About 10 to the 37 power molecules of iron are mined from the Earth's crust each year. If supernovae spin off matter via spherical symmetry, in other words, if the iron came from supernovae, an inverse square law applies, and how could that much iron accumulate in the Earth's crust?
Interesting question. Basically, it's because
and do we find similar amounts of iron in other planets? If not, why not?
The main answer to that is the fact that there's been enough time to do that. The universe is 14 billion years old, so there have been multiple generations of stars that have burned up. A typical large star will live maybe 10 million years. I mean, our sun will live 20 billion years, but a large, massive star lives, say maybe 10 million years, and then it explodes, and all of those ashes get spewed out into space. Most of them end up in dust grains. They condense, and as the thing expands, when things expand rapidly, they cool. That's how my air conditioning unit works upstairs. And so the sudden cooling causes condensations to form grains. And so then these grains mix in with all the gas and dust that's already there, and that sooner or later there's enough of this gas and dust that gets compressed by the spiral structure of our galaxy that the star can, that will start collapsing and form a new star, and those massive ones will then burn for 10 million years and then blow up. So if you're comparing 14 billion years with 10 million years, there's lots and lots of time to have multiple generations of stars. And you can move sort of 3 light years at, I think in kilometers, so excuse me. So you can, if you go a kilometer a second, in a million years, you will go about 3 light years in parsec. So a kilometer a second is kind of slow for stuff in our galaxy. So in a million years, you can be moving, you'll easily get to the next star. So the stuff mixes, it has enough time to mix because there are tens of millions of years for the stuff that comes off a supernova to mix in, and then for parts of that gas cloud that are nearby to form a new star, which has the guts of the iron in it. As to the abundances in other planets, as far as we can tell, those other planets have abundances similar to ours, except for certain elements, hydrogen, helium, and the noble gases, which will evaporate from the planet unless it's really big like Jupiter. So the relative ratio of the elements in the planets is not the same exactly. Mercury is different than Venus, is different than Earth, different than Mars, but the differences are really, really small. So if you take any gas and just take all of the hydrogen and helium and all the noble gases and take it out, what you're left over with is pretty much the same stuff: iron and nickel and magnesium and silicon and oxygen and carbon, all the common elements. So the planets will have somewhat different ratios of elements, especially if they're older planets, but they're not going to be that much different. They're still going to be made up mostly of oxygen, iron, magnesium, silicon, the things that are in the crust of the Earth.
Good, thank you.
Good question.
Jared asked, or rather followed up, thank you. I think a lot of us in 2020 wanted to hear more about your thoughts on the universe being a simulation. So apparently that's a especially interesting topic to the young people.
Yeah, no, it's a great thing to think about, but you know, the important thing to think about is how could you tell we were in a simulation? And you know, the people will also ask, well, why? You know, that's, well, you can't answer a why question, but just think about what it would mean to be in a simulation. What would give it away? And that's a great conversation to have over beer. And I've had this conversation or listened to this conversation many, many times.
Good. And there's lots of science fiction
Yes.
related, I know. Question from Brian Andrews: does cosmological expansion occur on small scales? For example, has our solar system expanded within its lifetime?
It's trying to, but the gravitational attraction between the planets and the sun is much, much greater than the dark energy pushing those two apart. So, you know, if I take a rubber band and I stretch it like this, the stretching actually produces dark energy, a very small amount, but it's much, much smaller than the elasticity of the rubber band. So I don't notice the dark energy because it's insanely small, but it's there. So the dark energy, yeah, there is dark energy between us and the planets, but it's totally overcome by the gravitational attraction. You may ask, well, at what distance does if you put a mass at some distance from our galaxy, how far does it have to be away before the gravity that of the object towards us, towards our galaxy, is equal to the dark energy pushing the two away? And that's on the order of a few, well, let's see, we do it in megaparsecs, so 300 million light years or so is where you begin to get a balance between the gravitational attraction and the gravitational repulsion due to dark energy. So it's only at very large scales does dark energy affect anything.
Thank you.
I'm
going to insert a question that occurred to me when I read your Wikipedia entry. which is that you were you make an appearance in Alan Alda's autobiography. And
Yeah.
I wondered if you could explain how it is that that came to happen.
So,
Alan Alda is a famous actor for certain generations. He was a star of MASH, and he's also quite, since then, had a second career in explaining science to people. So that's
and also
probably
and
something to do
also
with it.
having workshops and teaching scientists how to explain their stuff.
Teaching communication about
teaching
science.
communication.
That's right.
So Alan Alda came down to Las Campanas Observatory and Cerro Tololo. I was working at Cerro Tololo to interview us about the discovery of dark energy
In Chile.
and Chile, in La Serena in Chile. And, wow, this famous actor was going to come down and visit us. And I expected an entourage, but he shows up with Alan Alda, a sound guy with the rabbit on the end of a pole, and the director. And that's the show. That was Scientific American Frontiers, 3 people. And he liked it that way because the program would be fresh. So Alan Alda shows up, wow, I'm meeting a famous actor. And he's just a really charming guy. So we go up to the mountain, and he says, I don't want to talk to you about your science. We can talk about other stuff, but I want it to be fresh, because once you guys explain one thing, the first time, the second time, it's really boring. So he didn't want us to give away any of what our excitement was. So we went down to dinner. We went up and watched the sunset, and we went to the observing. It was part of the program to find exploding stars to measure dark energy to higher accuracy. And we were going to have him sit in front of the computer and actually discover an exploding star in a distant galaxy, which we could pretty much guarantee, because we look at enough sky that there's always going to be a new one that's very far distant galaxy. And he started saying, I don't really feel well. And he thought maybe he had eaten something that was hot. And then all of a sudden he said, I've got to lie down. And he went to the other room where there's kind of the observer's couch that we would sleep on when it was cloudy. And then he started screaming in pain. I mean, it was like, what's going on here? So fortunately, the Chilean laws are such that you have to have medical help on the mountain in terms of the trained nurse. And so the trained nurse came up. We put him in the ambulance, and we took him down to La Serena. It takes about an hour. And in the meantime, he's in incredible pain. And I called my wife saying, look, we've got a problem here. Alan Alda is really, really ill. We've got to find some sort of doctor who can help us. So we ended up taking him to the emergency room, and he goes in with the emergency room, and the emergency nurse is there, and she comes out and she says, he looks a lot like Alan Alda. And I said, he is Alan Alda. And she didn't kind of believe me. She goes back and she comes in. She said, that's Alan Alda? And I said, yeah. And she just turned white. It was amazing. And so in the meantime, we had to find a surgeon that could operate on his intestines. And it turned out he had an infarction, a blockage of an artery in his intestines, which is like getting a heart attack. But some people say it's the most painful thing that can happen to a human body. So we find this really great surgeon, and another amazing coincidence, this surgeon went into medicine because when he was a kid, his favorite program was MASH. So, here's Mr. MASH, and he's going to be operating on it. And so we're outside the emergency room, and the big doors that open where the ambulance brings in people. There was a guy in the corner that was being guarded by 2 guards with machine guns. And I didn't know what was going on, because Alan Alda was trying to save his life. And all of a sudden, I hear machine gun fire out on the street. And what had happened was that there's a prisoner that had stabbed himself and was injured, but not very badly, but it looked bad. And he was brought into the hospital. He had a friend come in a taxi, and at a particular moment, this guy jumped out of the bed and went into the taxi, and they went down the road, and the gendarmes were shooting at him. So after Alan Alda recovered from it, of course, he didn't know anything like this had happened. I said, that was really awesome. You and I participated in a prison breakout. And he recovered, and he charmed everyone. And for him, it was an epiphany, because as he was getting older, he was working more and more, and he was more concentrated on his career. And this was a shock, and he realized that he needed to enjoy life more, and he was going to cut back on what he was doing and concentrate on what he likes, which turns out is pretty much science and explaining stuff. So we're really fortunate that we have such a wonderful spokesman for science now in Alda.
Great story. Thank you. We'll go back to questions. Stanley Sokolow. Gravity waves stretch and compress through space, but we're in space-time, so do gravity waves also stretch and compress time?
Yes.
Would this affect the lifespan of unstable subatomic particles?
No, the effect is the effect is incredibly small. We call it the strain. For typical detection right now in a gravitational wave, the stretching, I'm going to talk about space, not time first. The stretching is about 1,000th the size of a proton. Okay, so that's very, very small. But then time will be dilated, but it's going to be dilated by that distance divided by the speed of light. And so that's a really small number. But it has to be taken into account in the calculations. So when they're calculating the resonances of the laser arms, they have to take into account both time dilation and the spatial contraction and expansion.
For the gravity wave detection.
Gravity waves.
Well, that reminds me of a question I intended to ask about, when we were young, Nick, the state of cosmology was such that the steady state theory was still advocated seriously. I would think it's fair to say that there's been a lot of progress in cosmology and understanding the history and future of the universe since then.
Yeah.
What does the next 50 years have to offer? What new instruments, for example, are being built that will revolutionize the field further? Or is the evolution of cosmology as a field, is it decelerating? Is it accelerating, decelerating, or not, or neither?
Oh, it's always accelerating. It's like the number of young people going into astronomy is awesome. And I'm glad I'm not young, because I couldn't compete with most of these people. There are a couple frontiers. I think the biggest frontier, I think the biggest question anyone can ask and answer is there life elsewhere in the universe? And we're going to provide resources in that direction. And within 20 years, we will have an answer to that question. If life is on another planet somewhere, if life happens in two different places independently, it's got to be all over the universe. So if we find life on Mars, and if life wasn't transferred from Mars to the Earth, or we find it on Europa or Triton or in a nearby star, then we will know that life is really common in the universe. And that's the greatest question, more than cosmology, more than understanding the universe. So lots of people are going in that direction, and I understand why. As for intelligent life, that's another matter about whether there's intelligent life in the universe. There are a lot of other things that are equally important. We still don't know what dark matter is. Our telescopes, we built mirrors up to about 10 meters across, but that size mirror is still not big enough to collect light to see the planets around nearby stars in any detail, or to see the galaxies that are the farthest away, the first galaxies that are forming, and the first stars that are forming and exploding in those galaxies. So the next generation of ground-based telescopes have mirrors basically from 25 meters across to 40 meters across. Those will capture enough light that we will have enough light to study those distant galaxies and see the first generation of galaxies, or to study the nearby exoplanets. In terms of cosmology, we call those the dark ages, because as you look backwards in time, the universe gets younger and younger. And at some point, you come to the point where you have the first galaxies. And if you look farther back in time, there's nothing. There's just hydrogen gas everywhere. And we haven't gotten to that transition from galaxies to the dark ages. So that one section is very, very important, because that's the beginning of light as we know it in the universe. So cosmologically speaking, that's really, really exciting. There are some other things in cosmology that remain to be understood. I think one of the most important ones is testing this theory of inflation, which is the third universe, by the way, which I haven't had time to explain. But there are certain predictions from inflation theory, not many, but certain ones that we've seen in inflation theory predicts or explains those, but they're things that is actually predicted, and we want to go out and we want to measure those things in greater detail. There are all sorts of other smaller but equally interesting issues, but I think the big questions are what's happening at the beginning of the dark ages, the end of the dark ages, and is there life elsewhere in the universe? I think those are clearly the most interesting questions in the future.
Is gravitational observations of gravity waves, is that going to be, the next frontier, the next type of observation that shows new things, or not? Is it?
Among other things, yeah. So right now with LIGO, we can measure things that have a certain frequency range, but it doesn't go to lower frequencies. So we can see black holes spiraling inwards and merging, but we can't see smaller objects like white dwarfs spiraling and emerging. So the gravitational wave people have this crazy idea called LISA, where they're going to launch basically LIGO, but put it into a orbit that orbits with the Earth, and they will have laser beams going back and forth over distances of kilometers, and they think that in outer space with all the solar wind and everything else, they can keep these things aligned to, again, a thousandth of the size of a proton. So they're building the prototypes of it. So LISA is funded, at least the prototyping, and probably will be built within the next 10 years. So that's for the gravitational wave physicists, that's very interesting. From more of a physics point of view, we still haven't measured the mass of the neutrino, and we are right at, not only is there this background radiation from the Big Bang, this cosmic microwave background radiation, there's also the cosmic neutrino background, and our detectors are very, very close to detecting the cosmic neutrino background. And the neutrinos temperatures will be a bit higher than the 2.7 degrees, which are the photon temperature. But these big detectors of a ton of liquid xenon, these sorts of things that dark matter people are building, they're getting close to detecting the background due to neutrinos. There are all sorts of, I say those are little compared to the first two things, but those are extremely important, exciting things to work on also.
It's another whole new kind of observation has never been done. So a couple of other questions here. From Jared, what do you think is the most probable source of the discrepancies in Hubble constant measurements? Are CMB measurements more reliable than other methods?
Yeah. So the problem, the question is asking about the expansion rate of the universe, the local expansion rate. And if you look at nearby galaxies, they look like they're moving a certain speed away from us. If you go to galaxies that are twice as far away, they look like they're moving twice as fast away from us. So there's a linear relationship between what appears to be the motion away from us and the distance. That's called the Hubble law. And the constant that's associated with that is called the Hubble constant, although it should be called the Lemaitre constant, because Lemaitre actually measured it 2 years before Hubble, but history is the way it is. So there are there are a number of different ways of measuring the Hubble constant, but the two main ways are just measuring how fast things are moving away from us or look like they're moving away from us locally. That gives you one number. The other one is to measure the physical state of the universe at this cosmic microwave background radiation, which you can fit a model of the universe with 6 parameters. And because the CMB is so well measured, there's very, very little error on those 6 parameters. So you can take the universe at that point and just then evolve it theoretically up until today using those 6 parameters that you've measured at the universe when it was 400,000 years old. But because those errors are so small, because the data is so exquisite, when you do this extrapolation till today, you also get a Hubble constant. And that Hubble constant is now much significantly different than the one that we measure locally by the direct expansion of the universe. So this is called the Hubble tension. And it's kind of, and although I measure the Hubble constant too, we're writing a paper on it right now. The real problem is, well, they use supernovae, exploding stars, which is a technique my group invented to measure distances in the universe. But it's not the supernovae, it's the measurement of the nearby galaxies that everyone argues about. But the people doing those measurements, they're Adam Rees and Lucas Macri in my university. These are people that are very careful, and I don't see what could go wrong with the local measurements. I'm not a person that works in the cosmic microwave background radiation, but you have to remember that they are extrapolating a universe from parameters that are set 400,000 years after the beginning of the universe till today. So anything weird that happens between then and now, that is a new law of physics appears or some fundamental constant varies, that's going to vary, that's going to cause that extrapolation to be wrong. So I think most people hope that it's somewhere in between the universe at 400,000 years until today, that there's some new physics that's going on there. And that new physics, someone's going to discover. So that's probably where the answer lies. But there are dozens and dozens of theories about what this new physics could be. But there's not enough evidence, because you got to measure stuff between here and there in great accuracy to measure if there's new physics. And people are doing that, but it's going to take a while to get the accuracy to the point where we can see if something weird's happening over this long stretch of time where we're doing the extrapolation.
Wow, I did not expect that answer. So I'm not up on this, obviously. Let's have a couple more questions. Stanley Sokolow asks, since large ground-based telescopes with adaptive optics, by the way, our alum Jerry Nelson had a lot to do with inventing that, the late Jerry Nelson, have such high resolution now, does that mean that satellite telescopes in the visible spectrum are obsolete?
No, good question too. No, what he's mentioning is that we are able, with these large telescopes, we launch laser beams parallel to the telescope, and those laser beams go up into the sky, and when they get to a certain level, they bounce off of the sodium ions that are in the high atmosphere at about 90 kilometers. So if you have a powerful enough laser, you can create an artificial star next to the field you're looking at. So if I'm looking at this in this direction and I create an artificial star over here, as this star twinkles and moves around, I can move the telescope in exactly the same way and take out the twinkling and the motion of the star. And so that's called adaptive optics. So we can take out the motions of the stars using this technique. The problem with the technique is the farther away the laser is from the telescope, the less accurate the correction is. So adaptive optics only works in a narrow field around the direction you're looking at. You've got to move the laser really close to that field. So if you want to look at high resolution over a much larger area, I mean really larger, you have to do it in space if you're just interested in the resolution of objects. But we go to space mostly to get out of the atmosphere, because the atmosphere blocks light in the infrared, it blocks light in the ultraviolet. So we build telescopes like the James Webb Space Telescope, which is going to be launched in November, that work in a region of wavelength between about 1 micron and about 50 microns, which we call the near and mid-infrared, which most of that is opaque here on the surface of the Earth. But out in space, it'll be completely transparent. And since light gets redshifted as you go farther back in the universe, all that interesting light that's emitted in the optical gets redshifted into that part of the spectrum, which we can't see from the ground. So the resolution, we can get the same resolution, we can get better resolution from the ground than in space, but only in a very narrow region. So things like the Hubble Space Telescope or future telescopes like the Roman telescope have much wider fields of view, and those are also important in the stuff that we do.
If we only didn't have a pesky atmosphere. Okay. Well, we've had a very interesting hour, I think. We're going to end with a question from my SSP classmate, Hank Rappaport, which is, I think, a good place to stop. Do you think we should be establishing colonies on Mars?
This is not necessarily a scientific question. I get annoyed at people that say because we're screwing up the Earth, we got to establish a civilization on Mars to save ourselves. I mean, we're screwing things up on Earth. We're going to screw things up on Mars. And we're going to another planet's not going to help us at all. So that's not the reason to go to Mars. And once we're at Mars, like, well, what are we going to do? You're going to live in a dome your whole life? What's the purpose of going there? Also, the trip is incredibly dangerous. You have any sort of solar event that sends uh, cosmic rays in your direction, you're going to kill the astronauts inside that, or they're going to get a dosage of radiation that's so high they're going to die of cancer. If is fortunate when we had the Apollo program that we had the Apollo program pretty much near a solar minimum, so the chances of of an event happening in that direction were less, because there are coronal mass ejections that we see regularly, once every a couple of months, that if directed between the Earth and Mars will produce a huge amount of radiation that could kill the astronauts. So you have to shield the astronauts. So that's one of the big problems that will get solved, but shielding means mass. So Elon Musk, who says we'll get there in 2024, I mean, he's crazy. He's just going to kill people doing that. And I mean, seriously, that's a really stupid idea. But why do we go to the moon? Why do we go to Mars? I can't come up with a scientific answer to it. But when I was a kid and I walk out in the fields in California, if there was a piece of wood lying on top of the dry grass, I'd always turn it over to see what was under it. There were cool spiders or snakes or whatever. You know, we have a nature to discover things. That's part of being a human being. And it's not just Western civilization, it's part of who we are, to discover things, just to turn over that board to see what's under it. And to me, that's why we're going to Mars. There's no good scientific reason to do it, but it's so captivating to us. When we landed on the moon, in that one moment, although it was the United States that got there, it really was mankind that got there, and it united mankind around the world. Everyone was watching it, and everyone felt proud of the fact that we went there. Americans, of course, because it was the US, but humanity felt that. And I hope that we can have another one of those moments, that when we go to Mars and land on it and human beings are there, that we also, everyone around the Earth will look up there and say, yes, human beings have gotten to the next planet. It's not scientific, but it's emotional, and it's something we can't deny in our soul.
All right. Well, I do think that's a great place to end, and really appreciate your time, Dr. Suntzeff, and look forward to your guest lecture this summer for our participants. And we will hope to see you again. We'll do this again with other guests in the fall, like I mentioned. So if you have ideas of who you'd like to see, anyone listening, then please let us know at sspalum@ssp.org. And
Richard,
yes, go ahead.
If I may say one more thing,
Sure.
is that I tell the students this too. If you have any other questions on cosmology, just email me. I mean, I'm like the only person in the universe with my last name, so it's really easy to find me. I'm more than happy to answer emails of people who have questions about science in general, but especially cosmology.
Well, we appreciate that very much. And this group of SSP alumni and former faculty is a great target for that particular message. I'm sure that a lot of people are interested in this topic, and I know I am. So again, thank you very much for your time this evening, and every summer coming back to us.
You're welcome.
All right. Good night.
Good night.